Okay, so we've reviewed this a little bit. Just going to briefly go through. So this says property of system of equations involving two linear. Remember we talked, you have one point of intersection. Those are all the ones that we've been doing. Or one set of solutions, right? If it's an application question. We have infinitely many if they're coincident, so parallel and coincident, same line. Or we have zero if they're parallel, and I call it parallel and distinct. Okay? So it's in the same booklet. Look again. So graph the following. Take a look at this. Has a slope of 2, and the second line has a slope of -2. What do you think? Are they going to give you 1 point, no points, or infinitely many? Do they have the same slope? No. Okay. They don't have the same slope. You'll get 1 point of intersection. Okay. So here, I'll just quickly do it. You don't have to do it. Oops, what's happening here? So -7, slope of 2. Will look like that when I join them up. And then 1 with a slope of -2. And you can see this is where they're going to intersect. Okay. My computer takes a long time to draw lines, so I'm not going to draw it right now. Okay. So 2 lines that intersect, their slopes are different. So that's the first set of statements here. So recall that when a system of equations has one solution, the lines intersect at one point. The slope of the lines must be different. So if they're solved for y, it's easy to tell. If they're not solved for y, then you need to solve for y. Okay? Next one, take a look at the slopes. Are they the same? Is a half the same as a half? Yeah. Yes. Okay? Are the y-intercepts the same? No. So these are going to be parallel, but distinct, I call it. They're going to be the same distance apart all the way along. So here, when I graph this one, then it's going to be up 1 to the right 2, so like this. And then the other one will be at y-intercept of 4, up 1 to the right 2. And I'm not going to join them up just because my lines take too long, but you can see they are parallel and the same distance apart all the way along, so that there are no points of intersection. So no solutions, the lines are parallel. The slopes of the lines must be equal, but the y-intercept must be different. And again, if it's solved for y in slope-intercept form, it's really easy to see. It's when it's shown in other forms that it makes it harder, and where you might want to solve for y so that you get it in the same form. And then infinitely many points. We'll take a look. The first one has been solved for y. So -2 y-intercept, slope of 1. So all of these points, again, I'm not joining them up because my computer's slow. And then this one, I need to divide both sides by 3. So when I do that, I get y equals x minus 2, which is the exact same line. Okay, so this is the same as the first one, just a different form. Okay, so these lines are coincident. So think about, if it's a coincidence that happened, it means 2 things happened that are the same. What a coincidence, right? So same with these lines, it kind of means the same thing. They're exactly the same line. So they're called coincident lines. The slopes of the lines must be equal, and the y-intercept must be equal. Basically, when you solve for y, it's exactly the same equation. Okay. So that's kind of a summary chart. Take a look here. Question 1, one of the equations is in a system is y equals negative 3x plus 5. Write another equation so that the resulting system has one solution. So your choice might be different from my choice. Basically, I want to choose a line that has anything other than negative 3. So I'm going to choose negative 10. And I could have the same y-intercept, but it doesn't have to be. Okay, so maybe I'll make it 15. Okay, some of you might be a little cheeky and give me y equals negative 423.7 x whatever, right? Because you want to be different, and that's totally fine. It's the same as long as it's different from negative 3. Okay, don't put negative 9 divided by 3 because that's negative 3, right? Always give it as a reduced fraction. No solution, that we have to keep it as negative 3, but then it has to be something different than 5. So now I'm going to use plus 15 because for sure it's different. Okay, but it has to be the same, negative 3. And then infinitely many, you can just write it out again, which is not very creative. You could put it in general form, which is a little more creative. Doesn't matter. Okay, it's just the same equation. Okay, so I'm going to skip question 2, just in the interest of time. Question 2 is a really good review of the last units you've done, because really these two, you want to rearrange them so that you can figure out the slopes. This one we know the slope, and this one we know the slope. But these ones we don't. This one we don't know the y-intercept, so you might want to solve all of them for y. Okay, so you're gonna do these. So I call them you do questions. Okay, you do. All right. Turn over to question 3. And this is, we talked about this before, what it looks like in certain situations. So this is a system. Who would like to use substitution for this? Who thinks that's the easiest method? No. I don't know. I think substitution. Really? Why? Why do you think substitution? Well, what would you substitute? Tell me. Well, I can't do that off the top of my head. Well, in this case, actually, you could use substitution, but use 3y, right? Because this is 3y, and then you could put it in. But typically, if there's no terms with a coefficient of 1, then I would use elimination, right? And in this case, you could, because it happens that there's a 3y in both. In any case, I'm going to rearrange this one to line them up to use elimination. So when I do that and get all the terms on the left, you'll notice that I'll just copy. So this I rearranged, this I just copy out. Okay, and if I use elimination here to eliminate x, I'm going to add. But what you'll see is it also eliminates y. Oops, because y is opposite in sign as well. So that goes to 0. This goes to 0. So 0 equals 3. Remember, we talked about that on the other day. Can 0 ever equal 3? No. Never, right? So you wouldn't want to have $100 and say, oh, yeah, that's equal to 0, right? Like, they can't. It's impossible. So this is where there are no solutions. So these are different. they will never be equal. Therefore, there are no points of intersection. There's no value for x or for y that could ever make those zero, because the terms go away. Okay, if you actually solve for x and y, solve for y, you would find the same slope and different y-intercept. So take a look at what's nice to know. If you have it in this form, if the x coefficients and the y coefficients are proportional, then you're good. They're the same slope, right? And that's a fast way of determining if they have the same slope. Okay, so similarly for the next one, let's see what happens here. The first one is, I'm going to leave it in that order. Alpha order. I'm going to bring the x over for the other equation. Okay. Now, I could eliminate either x or y by multiplying by 2, right? Or I could actually divide the second one by 2. You can divide if possible. 2 goes into all of that. But we typically multiply, so I'll multiply through. And take a look at the coefficients of x and y. They are opposites again. Oops, I'll maybe do that in blue. They're opposites again of the second equation. Now, in this case, when I add these equations, I get 0 equals 0. Well, now that's true, okay? And so it doesn't matter what you put in for x and y, it's always going to be true. 0 is always equal to 0, okay? So this is the case, so these are the same. You might end up, depending on how it's arranged, having 5 equals 5, or 3 equals 3, or 10 equals 10. In all of those cases, as long as the variables are gone, then if they're the same, they will have infinitely many solutions. Okay, because they're the exact same line. So if you can look at the coefficients and see that they're proportional, then you can know whether they're parallel, and then the constant term, they have to be in the same proportion to have infinitely many. Okay? All right. So then let's do question 5 and 6, and then you can do 7 on your own. Okay? These ones are solved for y, so that's nice. It says state the value of k such that the system has no solution. So no solution is 2 lines like this. What do we know about their slopes? The same. So what must k be? 3. Oh. No work, right? That's why it says state. Okay, they're already solved for y. So no solutions means slopes must be equal. Therefore, k equals 3. Okay. Take a look. The y-intercepts are different, so you know for sure that they're going to be distinct and not be infinitely many points, in case you're asked to analyze those, right? And then the last one here. So question 6 says, algebraically determine the value of k such that the system below has infinitely many solutions. Same line, right? This is one version of the line. This is the other version. So you could solve both for y. So if I do that, so basically get them in slope-intercept form. this one, actually, it's already solved for y. I just need to divide by 6, right? So that'll be y equals k over 6x plus 2. So we're comparing these two lines, okay? And so the y-intercepts are the same, which makes sense. They have to be the exact same line. The slopes have to be the same. So that means 5 over 2 has to equal k over 6. And so you can use cross product. 2k equals 30, k equals 15, or you can just use proportions, right? The denominators are 2 and 6, so 5 times 3 is 15, okay? But I want to show you just another way if these were arranged a little bit differently. If I, often they're with the x term first, and then the y term, and then either the constant term on the left for general or on the right. This is in improper general because it's got a negative, but I don't care about that right now. Then if I bring the x term over to the left, okay, then they're lined up, okay? And so now, if these have to be, well, either they're parallel and coincident or parallel and distinct, then we want to make this have the same coefficient of y, because that we have a number. So we would multiply by 3 to make it 6y. So that would be negative 15x plus 6y equals 12. And now we know that negative k has to equal negative 15. Okay? Because those coefficients have to be proportional, and now they're equal. So therefore, negative k equals negative 15, so k equals 15. So you could do it either way, okay? And that's why this method might be helpful for this equation, because then you don't have to solve for y, right? This one, maybe I'll go through it. This one, I would just multiply the first equation. Sorry, just a sec. I'd multiply the first equation by something to get the coefficient of x to be 12. So I would multiply by 4. So then that'd be 12x plus 4. Oh, what did I just do? 4, yeah. K, y minus 24 equals 0. And 12x minus 8y plus 5 equals 0. And now we know that negative 4k has to equal negative 8. We didn't have to solve for y. It saved a lot of time. So k is negative 2.